This is the second time I've made this video. Corrupted SD card. Woo! So, anyways, and I also have some problems with the camera. Hopefully this one's not kind of flashing in and out like you'll see in some future videos. But what we're going to be talking about here is the atmosphere and the rock cycle. You might think, well, what the hell does the atmosphere have to do with the rock cycle? Well, they do interact, right, in a pretty important way, although it's fairly slow. So what we're talking about here really is what we refer to as the slow carbon cycle. In the next video, we're actually going to stitch the fast carbon and the slow carbon cycle together. So, most of Earth's carbon is stored in rocks. If we went to gigatons, it would be, you know, millions, right? Some number times 10 to the 6th. We don't have an exact number. It's pretty hard to quantify, right? Like how many rocks are on Earth, kind of, and you know, think about crustal depths. But generally, there's really 3 types of rocks that store carbon. So those are carbon sinks, right? Store carbon for a long time. And then there's really one way that we have a carbon source from the rock cycle, and that's volcanic eruptions. So let's, well, this is a geology class in a way. I'm a geology professor, geography class, I guess. But you probably don't know that much about rocks. Maybe you've taken some geology in the past. If you haven't, you totally should. But we're going to talk about major rock types that store carbon. The first one, the primary rock type that stores carbon, is something called limestone. So limestone is a rock that's unique in the sense that it is primarily comprised of just one mineral. That mineral is calcite. The universal symbol for limestone is this kind of brick pattern. But calcite is a really important mineral. We use it for a lot of things, and when I show you the formula for calcite, you're probably going to recognize it. So calcite, it's a pretty important mineral. We use it for a lot of things. We use it for making concrete. And its chemical formula, if you were a chemist, you refer to it as calcium carbonate. So 1 part calcium, 1 part carbon, 3 parts oxygen. So calcium carbonate, that's a consumer, right? That's carbon, or CO2, that's trapped up in the rocks for, you know, a long period of time. We're going to talk about exchange, or we're going to talk about residence time here in a bit. So another type of rock that can store carbon is basically mud, or mudstone, or shale, or siltstone, all kind of the same thing. The mud rocks. If you have organic material like critters, zooplankton, phytoplankton, those things living in the water, when they die, first of all, they're consumers of carbon. They're made out of carbon. When they die, they settle to the bottom, and they can actually get buried in mud, and that carbon is now trapped in that kind of rock formation. So I'm going to go ahead and just call that shale. Like I said, there's a few different types of names that you could use. And then the last one that we're going to talk about is a rock that's made entirely out of plants. And so plants, when they die, particularly, you know, in marshy environments, they die in these kind of anoxic swamps and bogs, and that stops them from further breaking down, and they kind of just pile up. And so you get this organic material piled up and piled up and piled up. Maybe it gets covered with other sediment. Ultimately, that becomes a rock that we know of as coal. Santa may have brought you some last year, right? Famously. So those are the 3 kind of primary sinks of carbon. But what we need to talk about is how carbon gets from the atmosphere into these individual rock types. So I'm going to simplify some of the chemistry as I normally do. Again, I know that you're kind of probably doing backflips for your chemistry class. But actually, it's really simple. You know, these equations, you just balance the elements, so you know how things bond together. So some simple rules. What we're modeling here is actually rainwater, but I've left the hydrogen off for the carbonic acid that we've talked about because it does disassociate. and this is going to make the conversation really kind of streamlined. Here, this doesn't exist. This is kind of a chemical approximation of lots of different rocks, right? Calcium, silicon, oxygen, 3. That really isn't anything, but it kind of, in a bulk sense, approximates rock chemistry. There's lots of different individual reactions that we could look at. So what we have is rocks and carbonic acid. So limestone is really susceptible to weathering. Feldspars, which are mineral in granite, they're really susceptible to chemical weathering. And so when this rainwater falls down on these rocks, this chemical reaction takes place, and what happens is the rocks very literally dissolve in rainwater, although it's very slow. And the products in this case are calcite and silica. Both of those are soluble. Silica, also known as quartz, you've probably heard of it, and calcite. And if this were to happen on a continent, that water now contains dissolved calcite and silica, will flow down into the ocean. So we've got our weathering going on here, and it's bringing that material into the seawater, calcium carbonate, silicon dioxide, and a couple of cool things can happen here. One thing is that with water that has elevated calcium carbonate, little critters will actually absorb that from the seawater and then secrete it in mineral form, and we call those shells, right? Foraminifera, a couple of other things, you'll make their shells out of calcium carbonate, and so those critters live in the ocean, they die, their shells will sort of dissolve, but ultimately they'll recrystallize and form a rock type known as limestone. So in that case, just to kind of trace where we were, the CO2 that was stripped out of the atmosphere here by rainwater had a chemical reaction with the rocks and is now deposited on the bottom of the seafloor. So to have the conditions where you are kind of building a limestone factory, like I said, it turns out a couple of things have to be right. The temperature has to be right, the right amount of biology has to be there. So not everywhere there's huge volumes of limestone formed, but in some places. In other places, we have water that's really teeming with life. There we go. So we've got critters, right? Planktonic critters, which means they're just kind of floating around. We've got, like I said, zooplankton, which are animals, phytoplankton, which are kind of primary producers by photosynthesis. And so there's a lot of carbon caught up in the body forms of these organisms, and when they die, they settle to the bottom, and if there's kind of, mud or silt or something sloughing off of the continent, it will actually bury those critters in a shale or a mudstone, similar to limestone, although it didn't recrystallize like limestone does. And these shales will actually typically have a very dark appearance. They might even be like fine-grained sandstones or something like that. But if they have a high enough organic content, they'll start to appear really dark. So that's mudstone or shale being a carbon sink. So what I've drawn here is kind of a marshy environment. Hopefully you can understand that. We've got some trees and plants and water and all of that stuff. And what happens in this case is, first of all, again, we can go back to Earth's history and we think about, plants showed up in the Silurian. Cooksonia showed up about 450 million years ago. But by the time we get to about 310 million years ago, that's the first time that those little tiny plants, about an inch big, had evolved, and this is the first time we had forests on Earth, right? So vast forests with trees that are hundreds of feet tall. And that's kind of late in the game, right? Big woody trees were kind of not right on the forefront of evolution, right? Sharks have been around longer than trees, which is interesting to think about. But in this environment, especially, in the kind of middle Carboniferous time, There was also just kind of coastal marshlands all over the place. It was and so these marshes were all over the place. And what would happen is a tree would die and it would fall down into this kind of swampy marsh. And in that anoxic environment, it can't decompose. And it basically just has more trees fall on top of it, more trees fall on top of it, and pile up, right? So we've kind of met that before. But what we can look at is a chemical formula for a plant. So C6H10O5, carbohydrates, right? It's actually the same formula we looked at before. I've just kind of juiced the numbers a little bit. And in the case of coal, what happens is as this pressure is kind of continually, building and getting higher and higher, the sea level rises and falls. Maybe there's sediment deposited on this stuff. It actually drives water out of the equation. So let's actually take out 2 units of water. So 2 waters are gone. So C6H10O5 minus 2 waters is C6H6O3. And so, as you can see, the percentage of carbon gets higher and higher and higher. If we were to do that again, let's take out 2 more waters. We would end up with, now we're over here, C6H2O. And if we took 1 more water out there, you just get C6 left behind. And so coal is this kind of gradational rock, which is interesting. There's lots of different types of coal, and they're basically just different steps along the pathway, right? So anthracite coal, hard coal, which is kind of the highest grade, it's about 98% carbon, and oftentimes that 2% isn't water, it's actually other things that are also non-soluble. We've talked about pyrite and some of the other kind of accessory minerals that can exist within coal. Bituminous coal is the next one down, and subbituminous lignite peat, and then all the way back to wood, right? Just cellulose, which is kind of the starting point. So we just spent a lot of time talking about how rocks will sequester carbon. Limestone, right? I remember as weathering is going on, and that weathering process itself is stripping carbon out of the atmosphere. Can pile up in mudstone, be part of the structure of limestone, and then also coal, right? Where plants essentially can't decompose, and they pile up and get compressed, water gets driven out. The other thing that we need to talk about is the backside of that, right? The carbon from the rock cycle back into the atmosphere. And generally, a good way to kind of take a look at this is through the process of subduction. And this is kind of a big idea in the context of plate tectonics. We have a thin, fairly heavy oceanic plate colliding with a thick, fairly buoyant continental plate. And what happens is the oceanic plate gets shoved underneath. It's kind of day 1, it's actually day 2 physical geology class. But you can see here, I've sketched out a kind of schematic diagram of what we would call a subduction zone. But I've added a little bit, right? So here, got our little fish there, so we know that's the ocean. And I've got our oceanic plate subducting, but I actually even added a little bit of limestone, right? So a little bit of carbon hosting rock, or actually limestone is a rock that we call a carbonate. It could also be oil shale, or shale that has a high organic content. And as that gets shoved down into the earth, it gets heated up. It's pretty hot down there, and that generates melt. Also, everything is waterlogged, right, because it's coming out of the ocean. And that magma that's sourced rises through kind of buoyant force up through the continental crust, and we get a volcanic eruption that spits stuff out, along with the rock material that it's spitting out. Right? Most of what it spits out is rock material, but gases, mostly water vapor, right? The vast majority of what a volcano spits out is water vapor, but CO2 as well. But CO2 isn't the main thing that a volcanic eruption kind of ejects into the atmosphere. So this is kind of, again, the return, and using this big number that we've said over and over, about 1/10 of a gigaton of carbon, right? So 0.1. So it's important And it really is, again, the slow carbon cycle. Now, this number isn't really something that can change on the human time scale, but it does change. So if you think about kind of the globe, or you like imagine a globe in your head, there can be times in Earth's past where we have a situation where there's more subduction happening, more seafloor spreading, higher rates of volcanic activity, and we have seen that kind of fluctuate very slowly over Earth's kind of geologic history. So if you had a period where you had increased volcanic activity, this number might go up a little bit. But actually, one of the other interesting things is if we kind of go back to plate tectonics and we think about what happens if two continental land masses collide with one another. In that case, they can't subduct. India, the subcontinent, was kind of heading north, and it's on its own plate. And about 40 million years ago, it collided with southern China, and the result is the Himalayas, right? So the Himalayan mountain range is about 40 million years old and still growing. But how does that play into the rock cycle? Well, when you stick rocks up to 26,000 feet, or however, something like that, the summit of Everest, it not only interacts with the weather patterns in the troposphere, so it can draw in a significant amount of moisture, but it also really increases weathering rates, right? So sticking rocks way up into the atmosphere, they tend to weather much faster because there's more water coming down. And remember, we talked about that weathering process is the negative sink, right? So more mountains actually make this number go lower, right? So you would have a decrease in carbon in the atmosphere from the rock cycle with mountain building, and it could increase with increased volcanic activity. Okay, that should do us up for the old slow carbon cycle, and now we're going to put it all together and start to think about residence time and how long it takes a change in that carbon cycle to kind of normalize or to kind of even itself out. And it really depends on the different residence time in different parts of the carbon cycle. Okay, I'll catch you then.